Bien. Je vous propose de commencer cet exposé, le dernier de la série de 4 que donne Naama Friedmann au Collège de France. Merci beaucoup, Naama, d'être présente avec nous. I will switch to English because this is our shared language, maybe easier than French. So welcome to this conference, which is performed in association with the cycle Acting for Education, Agir pour l'éducation du Collège de France. You can find all the lectures of the cycle Agir pour l'éducation online. There was a series of lectures this year on how to act for mathematics. And today we inserted this special lecture because Naama was visiting and because she has extremely relevant data on how numbers are organized in the brain and how they can be separate in separate pathways from letters. And of course, both aspects are extremely important for education. Naama Friedmann is a professor in the Department of Education in the University of Tel Aviv. And I would like to mention that she is one of the world's most renowned neuropsychologists to these days. I think this is important to stress because neuropsychology used to be the main road to understanding the relation between brain and mind, the study of patients and how their impairments clarify how the system, the cognitive system could be organized. And it was superseded in a sense by brain imaging. But brain imaging does not always afford the same sort of quality inferences that neuropsychology with very particular patients affords. And Naama has been keeping this amazing tradition of finding very interesting patients, studying them in great detail. Other people do so in the world, and we could mention, I don't know, Alfonso Karamazza or many others, Max Coltart, who inspired a lot of your model on reading. But I would really like to say that I think this is Naama's extraordinary talent, is to draw the most out of observations, very careful observations from patients, and we see some of that today. And if it's difficult to introduce you because you have so many interests, and I don't want to be too long, but I think after working with you for a little while, I understood that you have at least 3 loves in science, and we'll just stick to science. The first one is the love of a good scientific discovery. And I think we'll see some tonight when you find quite unexpectedly that somehow two things dissociate. The patient does jargon, but he doesn't do so in numbers. We'll see some of that, other observations. The second great love, I think, is the love of great stimuli. It may not be known to everybody in this room, but in cognitive science, we spend a lot of time designing experiments, and that involves selecting words, selecting contrasts. And I know you love to do that, and you do it extremely well. And we've done it a little bit together as well, for which I'm very grateful. But the third love, I think, is even more important, is the love of the patients themselves. And that is very special. When I met Naama, she remembered the names of the sons and daughters of some of the patients that she's worked with. And we discussed that recently. Some people, I was told the same thing, by the way. Why are you interested in what could help the patients or how to rehabilitate? Re-education is a different department from neuropsychology, and it's not interesting in theory. But that's not at all your attitude, right? And your attitude is really to care about the patients and to see what could help them, and in particular, what could help them to reacquire some of the things that they've lost or to go around the deficits. And in passing, it turns out to be extremely interesting for the theory as well. If you find the right way to address a deficit, you may have shed some light on the organization of the pathways that led to that deficit. So Naama is very passionate about her patients. She knows them by heart, I should say. And she is extremely keen in finding ways that they can be helped. Not just the patients that we're going to see tonight, but also I think in previous lectures it was clear, patients with intracranial surgery, undergoing intracranial surgery, and having to decide very, very quickly how to avoid language circuitry and so on. This is a very massive amount of work at the borders between linguistics, reading, mathematics, and I think it's a very extraordinary set of lectures that you've given us in this past 4 weeks. I repeat, they're all online. Those of us who missed some of them can all watch them. They're really very, very well designed and careful. So help me welcome Naama. Thank you very much again for being here.
Thank you very, very much for this kind introduction. What I want to share with you today is some work on numbers and words. And I think maybe the main question, when we talk about education, the main question that I want to ask is, when we have a child coming with dyslexia, with a problem in reading, do we expect them to have also a problem in numbers? And vice versa, if there is a child coming with difficulty in reading numbers, do we expect them to also have problems in reading words? So for education, this is extremely important, because we want to know whether we expect the child to have additional problems. But it's also important for theory, because if we find out that there are dissociations, that there are differences between reading words and reading numbers, between saying words and saying numbers, it will say something very important about the process, about the model of reading numbers and about the model of reading words. So this is the big framework in which I'm going to work, and I'll tell you the details as to how I'm going to do this today. First of all, I'm going to show you several specific types of reading impairments, of specific types of dyslexia, and show you, I'm already giving you the results. It's not a good spy story, but I'm going to show you people who have very severe problems in reading words, but they don't have problems in reading numbers. Then I'm going to show you people who have problems in reading numbers without problems in reading words. And in the end, I'm going to shortly say something about people who have problems in both, but the problems look differently. So the problem in saying words is different from the problem in saying number words. So these are the details. I'm going to talk about 3 types of dyslexia. I'm going to talk about 2 types of number reading impairments, and then in passing about 5 more. And then I'm going to talk about phonological production and comprehension and input problems in developmental cases, in acquired cases, and in sign language. Okay, so I'm going to start, and I'm going to start with, as I said, individuals who have dyslexia. So they have problems in reading words and non-words, and asking whether they have problems in reading numbers. So what you see here, this is the model for a suggested model for reading numbers. What we have here is a suggested model for reading words. And I'm going to show you patterns of impaired word reading with good number reading. Now, I'm not just going to point with my whole hand. I'm going to point with my finger. So let's say something about the process of reading. I apologize for those who have been in my previous lecture where I talked about types of dyslexia. I'm not going to say exactly the same, but the spirit is similar. So when we read, the reading is a process that starts from a written word and gets to comprehension of this word and to reading aloud of this word. And this process has several stages. It has multiple stages. The idea when we talk about reading impairments and when we talk about dyslexia is that each of these stages can be selectively impaired, and it can give rise to a different kind of dyslexia. And this is how we get to multiple types of dyslexia, each resulting from a deficit in a different point in the model and having a different patterns of errors. So why is it so? Because the different processes are represented in different areas in the cortex. So impairments in different places give rise to different dyslexias, and also some of these has to do with impairments in the white matter, in the tracts that lead from one cortical area to the other. And the result is different patterns of errors. So we can see, so it is not enough to say that a person has a reading impairment. It is not enough to say that someone has dyslexia. We want to make sure that we understand exactly what kind of dyslexia. And this maybe boils down to what Stan named love of patients. If we want to help patients, just knowing that the patient has dyslexia doesn't tell me how I can help them. If I want to know if this patient has a problem with reading non-words, I'll teach them how to convert from letters to sound. If this patient has a problem of letters migrating between words, I'll present one word at a time. So I want to know exactly what is the basis of the dyslexia in order to understand how to help the person. And of course, it also has a lot of theoretical implications. So when we look at impairments in different positions in this model, we can see different kinds of dyslexias. So today I'm not going to talk about dyslexia with or without problems in reading numbers. I'm going to talk about dyslexias with and without problems in reading numbers. So the procedure that I'm going to take is identify a specific function in word reading, understand what the parallel is in number reading, and then test this parallel in number reading. So for example, if we talk about problems in the relative order of letters within a word, I will look whether this person has a problem in the relative order of digits within a number. Okay, so I'm going to point with my finger and not with my whole hand. So I'm going to talk about problems in letter position, in letter identity, in letter-to-word binding, and later also about the phonological production. So because I felt bad that some of you were in my previous talk and you already heard about this dyslexia, this is going to be a riddle. What kind of dyslexia is this? So what you have here are people, French speakers and English speakers who make errors. Now you look at the target words on the left and the result on the right. Some of you know these persons in person. And then just notice what kinds of errors you can see in this. And I see that you already see that the errors are actually letter migrations within the words. So the letters are identified correctly. They don't migrate between words, but their position within the word is incorrect. And this is called letter position dyslexia, because the deficit is in letter position, and most of this work in Hebrew I've done with the Aviv. So what the properties of this dyslexia is that the predominant type of error is letter migration. And it affects not only reading aloud, it also affects comprehension. So people understand the word as if it was transposed. So if they see the word slime and they understand it as smile, they will define it as something positive and not as something negative. So I always recommend reading slime as smile. And also, when we look at where these errors happen, they mainly happen in the middle of the word. So most of the errors involve only middle letters, and the first letter and the last letter are usually robust and do not change their places. And in the beginning, this dyslexia was identified in 2 cases of acquired dyslexia, of Hebrew readers with acquired dyslexia. And later, we also identified several hundreds of individuals with letter position dyslexia who are Hebrew speakers. Of these 318, I counted yesterday, one by one, 318 had only letter position dyslexia, so without other kinds of dyslexia. And this is a relatively common type of dyslexia. It's the 3rd most common dyslexia in Hebrew and also in Arabic. Now, when we look at this dyslexia, there is another property that is quite important, which is when we look at what kinds of words are susceptible to errors, and we compare words like from, that can, in which letter position error results in form, and we compare it to a word like frog, where it doesn't result in any existing word, we can see that there are far, far more errors in words like from, which we call migratable words, because a migration of letters within this word results in other existing word. And there are very few errors in words like frog that are non-migratable, which means that it's really important, in order to identify this dyslexia, it's important to use migratable words. And when we use migratable words, this type of dyslexia was identified already in quite a lot of languages. Specifically because we are in Collège de France, in Agir pour l'éducation, we can talk about French. And in French, there were 2 researchers who were working some of their work in the desert to come up with lists of migratable words in French. And this was very fruitful because we found individuals, together with Cassandra Poutier, Watkins, and you can see the paper also, we found individuals who speak French and have letter position errors within words. We also had the same work in Italian, and 2 papers that were published together with Daniela Traficante and Claudio Luzzati. And we found quite a lot, 6 of the population of dyslexics who speak Italian show letter position dyslexia. I want to say something about Claudio Luzzati. Claudio Luzzati passed away yesterday. He was he was a neurologist. He was one of the greatest cognitive neuropsychologists. He was the kindest, most sweet person. He really cared about his patients. He worked a lot on treatment, and we're going to miss him a lot. Sorry. I'm sure he's sitting somewhere with the angels, discussing how they can make the world better now, more healthier for people. With the angels, exactly. Okay, so now we get to the question. So I introduced to you letter position dyslexia, and now I want to get to the question: what is going on with numbers when we talk about individuals with letter position dyslexia who have problems in reading words? Do they have the same problem in reading numbers? How do we do it? We take individuals that we know they have only letter position dyslexia, and we look at numbers that are very similar in their properties, the same number of digits as the number of letters, and we see whether they make transpositions in these numbers too. Why is it important? As I said, it's important for clinically to know what to expect from a person with letter position dyslexia, but it's also important theoretically, because we want to know, when we talk about this reading model, does it treat only orthographic material, or does it also handle numbers? Okay? And the way we do it is we look whether letter position function that we know is impaired also affects reading of numbers. So we gave our participants who we already knew had letter position dyslexia. We gave them 90 multi-digit numbers, 4, 5, and 6 digit long, and we compared them to 4 to 6 letter words. And we already selected them according to the fact that they have letter transpositions in words. And what happens in numbers? They are normal. They show exactly the same percentage of errors as do individuals without any problem. So what does it mean? It means that they make a lot of transpositions of letters, but no transpositions of digits. Also, when we look not only at reading aloud, we look at same different decisions. So we show 2 words, slime and smile, and we show two numbers that differ in the order of letters. We see that they succeed in same different decision of numbers, but not of words. So we see a dissociation here. Letter position dyslexia affects letters, but not numbers. This is what we did in Hebrew, but we did the same thing in Turkish. And this is work with Selçuk Güven. Again, we created lists of migratable words, and we tested several hundreds of children in school, in elementary school, Turkish speakers, and we identified 55 Turkish-speaking children who have letter position dyslexia. Okay? They make the classical letter position errors. And when we look at the reading of words and the reading of non-words, they all make quite a lot of migrations. And then we presented numbers. We presented them 40 multi-digit numbers. Now the number of, so you'll see again the words and non-words in purple, and you'll see the rate of digit position errors in numbers in orange. And it's not surprising that you don't see almost any orange. Okay? It's because they don't make transpositions in numbers. So you see very, very few transpositions in numbers, and most of them, so only 3 children had, I think, 1 transposition, and the rest had 0 transpositions of digits within numbers. So you see again the same dissociation. Letter position errors, no digit position errors in the same individuals. Well, a lot of statistics and numbers here, but the main idea is the following. They make significantly more transpositions in words than in numbers, and they don't differ from the controls in the number of digits and the rate of digit transpositions. They do differ from the controls in the rate of letter position errors. Yes?
Excuse me. If you ask them to spell a word, do they do migration errors?
Most of them don't. So the question was, what happens in writing or in spelling? So in most cases, we did, for Turkish, we did it only for some of them, but for Hebrew and Arabic, we did a lot of writing testing for, and Italian also, a lot of writing testing for individuals who have letter position dyslexia and other dyslexias. And in most cases, you see a dissociation between reading and writing. So in most cases, the person might have another dysgraphia, but it is not the same type of dyslexia and dysgraphia. So most of the individuals who have letter position dyslexia don't have letter position dysgraphia. Okay, so what does it mean? What we see from Hebrew letter position dyslexia and from Turkish letter position dyslexia is actually that there are two different processes. One that is handling letter position and the other that is handling digit position, and I want to suggest that these are parts of two separate processes. One orthographic and the other is dealing with numbers. So this is one theoretical implication. The other implication is that sometimes people say, dyslexia is a visual problem. It's a problem when the letters are close together. So dyslexia doesn't seem to be a visual problem, right? Because if it had been a visual problem, then we would see the same problem in numbers, and we don't. And of course, this is surprising, right? Because if you we think about what I showed you is developmental cases, so individuals who have letter position dyslexia from birth. And still they show this dissociation between numbers and letters, right? So this is quite surprising to see two relatively new in evolution cultural inventions that are dissociated. And there are beautiful work also by Stan asking this question of how come there might be different circuitries in the brain that deal with these with numbers and letters. And the idea is that there are differences in connectivity. So words relate to language areas, numbers relate to quantity, and this might be what underlies the fact that we see this kind of dissociation. Okay, I'm going to show you another dissociation in another language, a language that is not printed, sign language. So, or more correctly, finger spelling in signers. And this is work with Neta Chalutz and Doron Levy, my PhD students. And the idea is the following: when we look at individuals who sign in sign language, usually each sign corresponds to, in spoken language, to a word. So we have something like light, or rain, or snow. And when we have to introduce a new name, for example, if Stan doesn't have a name in sign language, in French sign language yet, then we have to improvise. You have to find a way to mention Stan without his sign. So in Israeli Sign Language, for example, we will, or in many languages that use finger spelling, we will say S, T, N, Stan. So we will finger spell the letters S-T-A-N. Okay? Now, of course, this is reading. If you need to look at the finger spelling and understand what the word is, you have to read. In this case, you don't read written material, but you read the Hebrew letters as they are, or the relevant spoken language letters as they are signed with the fingers. And this is quite common. It's used for various kinds of names, street names, brand names, etc. So the question is whether we're using the same process for finger spelling. And we do it again through work with individuals who have, in this case, letter position dyslexia. And these are two signers, native signers, Alon and Yona. They are relatively young, and they have letter, when we test their reading, they have letter position dyslexia in reading written words. And then we want, first of all, to see whether they have letter position dyslexia also in finger spelling. So how do we do it? We show them a written word, or we show them the same word in finger spelling, and we ask them to sign it. So if the word is a house, we ask them to sign it. Okay? And it could be also that the word is written and they have to sign it. And when we compare their performance, this is percentage of errors in written words compared to the controls in lavender. You see that both of them make far more letter position errors in written words, but they also make far more letter position errors than the controls in finger-spelled words. Okay, so both of them have letter position dyslexia, not only in reading written words, but also in reading finger-spelled words. And the properties, it also affects the response time when they have to match a written word or a finger-spelled word to a matching picture. So to decide between smile and slime, for example. I don't know how exactly you would take a picture of slime, but if you show the two pictures and you ask them, and you show the word smile and you ask them to select which picture it relates to, it also affects their response times. They take longer to decide about migratable words. And they, like in spoken languages, they have problems mainly in the middle, and they make more errors in migratable words. So the first conclusion is that signers are using the same kind of process that individuals who read written words use. And now we get to a question of today. Do they make transpositions also in numbers? So we tested their number reading. Signed number reading. And I'll just mention something about numbers in Israeli Sign Language. So the digits, I think you already understand digits in Israeli Sign Language, right? 1, 2, 3, 4, 5, etc. The multi-digit numbers have some kind of morphological structure. So for example, this would be 20, this will be 200, and this is 2000. See? So you see the hand shape is the number, and then there is a morphological structure coded by the movement of the hand. Okay, so what do they do when they read numbers, multi-digit numbers? So I remind you that they had letter position dyslexia in words. This is the percentage of errors that they made, transposition errors that they made in words and in numbers. Ekochi. So this is what they do in numbers. They don't do transpositions in numbers. Again, not a general memory problem, not a general visual problem. They have a specific problem in letters. Okay, so at this point, we already have evidence also from sign language. So we have evidence from Hebrew, from Turkish, and from sign language for the dissociation between letter position errors in words without digit position errors in numbers. Okay? Now we move to another dyslexia. So until now it was letter position dyslexia. I'm moving to another dyslexia. It's called attentional dyslexia, and the reason it's called attentional dyslexia is that it has nothing to do with attention. But maybe in 1977, Shallis and Warrington, who found this dyslexia, they thought it was related, and the name remained. Okay, so I'm going to have we are going to do a little experiment. Okay, I'm going to show you the words on the screen for a very, very short time. And you're just going to tell me what you saw. It's going to be in English. I think Hebrew would be less useful for you. Okay? Are you ready? It's going to be really fast. Normal readers are going to have difficulties with this, with how fast it is. Okay? Ready? Goat, coat, coal, Goal? Anything else? Okay. So there were 2 words, probably I can tell you that it was indeed 2 words out of these 4. Okay, maybe the next one will be easier. Are you ready? Heel. Heel. Read. Head. Okay. Okay, one more. Last one. Ready? Okay. Wild mind. Anyone saw something else? Mind. Anything else? Mild. Okay. Okay. Now, this is not dyslexia. This is normal reading under very short exposure times. Okay? And this is something that shows that you are normal, that we are normal. Okay? Finally, something that shows that we are normal. The first one didn't include quote and didn't include goal. Why did some of us see quote in the second word? We were able... Exactly, exactly. Sarah saying T appears in the top word. So we identify the letters correctly. We identify the order of the letters correctly. But what we don't manage to do in 100 milliseconds is to bind the letter to the word in which it appears. And this is why the T is there. It's just not in quote. Okay? But because we don't manage to, in this time, to bind letter to position, we see quote. So this is what we call migration. What about, was there a head in the next pair? No, but now we already know why we saw head, right? Because we identified the letters correctly, and we identified the order of the letters correctly, but what we didn't have time to do is bind the letters to the words, and this is why we had, again, migration of the final letter. Okay? As for the last one, there was no mind, although people like you who sit here in this lecture would be interested in the mind, right? So this also might affect what you think you saw. But the reason why we see mind in the second word is because we identify the letters correctly. We know that D is the last letter. We just don't know last letter of what. So it might be the last letter of the second word. Okay. So there is no mind, and I thought you would think about wine, because after all, we are in Collège de France. But okay, you thought about mild and about mind, so I'm happy. So what we see here is something that happens in normal reading, in unimpaired reading, but individuals who have attentional dyslexia are unable, even if you show them these words for an unlimited time, they identify the letters and the order of the letters, but they are unable to bind the letters to the word in which they appear. And then we see the same errors that we made here, we see the same errors when they read without any time limit. So this is an example from our work with Stan and Cassandra. So instead of reading, why is the last pair read instead of read as donk? Because the C migrated from the second word, right? And the same for the others. You can see migrations between words that preserve the position within the word. And when we look at the properties of this dyslexia, also a very common dyslexia, the fourth most common dyslexia in Hebrew, for example, we see that the letters migrate from the top and the bottom words, and from the words on the right and on the left. And another thing that is really important, and also important theoretically, is that the letters preserve their position within the word. So if it was the last letter, it remains the last letter of the new word. If it was the second letter, it remains the second letter. So it keeps the position within the word. So it shows us that there is a dissociation between letter position within a word, encoding of letter position within a word, and the binding of letters to the word in which they appear. So it means that there are two separate functions. There is another way to show that there are two separate functions, and this is the double dissociation between letter position dyslexia, which affects letter position, and attentional dyslexia, which affects letter-to-word binding. And indeed, this is a result of what I counted yesterday. We see 318 individuals with letter position dyslexia without attentional dyslexia, and 158 individuals with attentional dyslexia without letter position dyslexia. So clearly, these are separate functions. Okay, and now for our question. What about numbers in attentional dyslexia? Do they migrate the same as letters? Again, we want to ask whether the same process applies both to orthographic material like words and to numbers. So how do we do it? This study we did with individuals with Parkinson's disease. So we are working, some of my students who are speech therapists work in a very nice institute for individuals with Parkinson's disease. I was very, very happy to hear that there is speech therapy in this institute, because usually they get psychological therapy and physical therapy, but not language therapy. So I asked them, what are you doing with these patients? And they said, voice treatments. And I said, yes, but what about language? And they said, B. So I asked, what are the problems that they show? And they said, so this started a whole new project of assessing various kinds of language abilities in individuals with Parkinson's disease. And we tested syntax, and we tested lexical retrieval, phonological abilities, reading, writing. So for reading, we tested their reading of words and non-words, and also of word pairs. So these here, 62 patients read 152 words presented as migratable word pairs, which means that migration of a letter between the words creates other existing, may create other existing words. And when we ran this task, we were very, very surprised in the first 20 participants, but then when we got to participant number 62, it was already expected. Most of them have attentional dyslexia. Most of the individuals with Parkinson's disease that we tested, which were not selected on the basis of problems in reading, and actually never reported that they have migrations of letters between words, have attentional dyslexia. So first of all, this is, I think, an important finding, because this requires some kind of treatment, some kind of instructions for the patients how to read in a way that will be easier for them. But then we ask, what about numbers? Because the first thing, when you think about Parkinson's, maybe there is a problem with the muscles of the eyes. So maybe it's something that is completely motor in the ocular system. So we tested the reading of numbers, of number pairs, to see whether there are migrations of digits between numbers. And the way we created the stimuli, the number stimuli, was we just made sure that we have exactly the same numbers with the same properties as the words. So for example, if the same letter repeated twice in the same word, then we substituted it with the same digit. Okay? If there was a vowel letter, we substituted it with a 0 or a 1. So we actually had exactly the same properties as much as we could of numbers, number pairs, that would correspond to the word pairs that they read. So we created a list of number pairs. And what did we find? So in red is reading words, that is significantly more migrations between words compared to the controls. And then on the right, you see numbers, and all the light blue is numbers that are read without any migration or with a normal rate of migration. So very, very, very clearly, what we see here is that individuals with, out of the 33 individuals who showed attentional dyslexia in reading words, 24 had, all of them except for 3 showed no migrations of numbers. Okay? Again, a very clear dissociation. Very clear dissociation between migrations between words without migrations between numbers. Okay? First of all, then it can't be something that has to do with the muscles of the eyes. It has to be something else. But secondly, it shows, again, a dissociation between letter-to-word binding and digit-to-number binding. It shows that these are two separate processes. Look at this guy. He made 74% migrations between words in the word pairs and 0 migrations of digits between number pairs. So it's very, very, very clear. Okay, so I conclude attentional dyslexia but by saying migrations between words, not between numbers. And I'm moving to the next dyslexia, yes.
For attentional dyslexia, is it most likely to migrate between the first letter and the last letter, or?
When you look at properties of attentional dyslexia, there are twice as many migrations from the first word to the second word than from the second word to the from the second word to the first word, and there are more migrations of the last letter in comparison to the first letter. So it's graded. All letter positions are susceptible to errors, but the last letter and the second word, be it the right word or the left word, depending on the language, are more susceptible to migrations. Okay, and now I'm moving to developmental neglexia. This is work that I've done with Ivana Nachman-Katz. And in general, when we talk about neglect, another topic that Claudio Luzzati did incredible work in is when we look at general visual spatial neglect, this is a plate of one of my patients who finished eating. Okay? He thought he finished eating because he finished eating everything that he paid attention to, which was the right side of the plate. But on the left side of the plate, he couldn't shift attention to the left side of the plate, and he didn't eat it. And then what we do is just we turn the plate 180 degrees, and then they eat what they thought before was done. And when we look at individuals with general neglect, visual spatial neglect, we also see that when we ask them to circle all the lines that they see, they omit the lines on the left. When we ask them to draw a clock, they usually draw the whole circle, but they omit the digit on the left. And this, I showed it in a previous talk. This is one of my patients who tried to draw a clock, but he remembered that there were 24 hours in a day. So what he did, he tried to put all the 24 hours, but on the right side of the clock, and some of them became a bit delayed, fell outside of the circle. When we ask them to copy, we see two patterns of errors in copying. One is if you have 4 objects, they might omit the left 2 objects. And the other is that within an object, they might omit the left side. And what I'm going to talk about today is something that is more similar to omission of the left side within an object in word reading. So in word reading, when we have neglect dyslexia at the word level, what we see are errors on the left. It could be omissions, but it could also be substitutions, and it could also be even additions of letters on the left. I know that most of you don't read this language. Professor Dan does, but I know that there are many who don't. But just look at the target. The target is on the left, and at the result on the right. And you can see that the 2 letters on the right are correct, and then the last one is either omitted or substituted. So this is what characterizes errors in neglect dyslexia, errors on the left side. And when we tested, Ivana Nachman-Katz and I tested individuals with developmental dyslexia, we saw 21 children who had developmental neglect dyslexia at the word level. So they were making errors on the left side of words. And of course, now we want to ask, do they make errors on the left side of numbers as well? Again, it will say something about the model. Okay. So first of all, when we tested them in general neglect, in the general neglect battery, I see it's not very useful. The titles of the columns are not very useful. I apologize, but this is not important. The most important thing is that they don't have general visuospatial neglect. They have really dyslexia that affects only, at this point we don't know, that affects sequences, let's say. And then we tested their reading of words, and we compared them to lists of symbols. And what we see is that, and you can think that, you know, when you see words, that there is some connection between the letters because they create some kind of whole. The different symbols don't create any kind of whole, but you can see a huge difference. So it's clearly not a visual problem and clearly not some kind of general attentional problem. They make a lot of errors in words. They are completely correct in lists of symbols. Okay? But still, lists of symbols, it's not the same as numbers because symbols don't create a sequence that is a unit in some form. So we wanted to test numbers. So we showed them numbers of the same length as the words in which they made errors and tested whether they make neglect errors on the left side of the numbers. Well, they don't. So you can see the average of 41% neglect errors in reading words and 1% error in reading numbers. Again, we see a very clear dissociation. But then what we did, we took it one step further, and we used this kind of stimuli. So do you identify the number here? 7,109,179. Any Hebrew reader here? Okay, for Hebrew readers, it says professor. So the letter on the right is P, the one that looks like 7 is R, the one that looks like 1 is O, and it says professor. Okay? So what we could do in Hebrew is show exactly the same sequence and ask the patient to read it as a word or to read it as a number. And the difference, it's exactly the same stimulus. We just give different instructions. Okay? So we give a list. It was really fun. We created a list of 11 words that could be written as a number. And then we told the participants, please read this list of words, or please read this list of numbers. Okay? So this is, for example, what you might think is 7,979. But when you read it as a word, it is a butterfly. Okay? Parpar. So we compared the reading of the same people, of the same stimuli when they interpreted it as a word or when they interpreted it as a number. And what we see is a huge difference again. So when they read it as a word, they made a lot of neglect errors on the left. When they read it as a number, almost no neglect errors on the left. Okay? So I'm summarizing the part of the dyslexias. We see letter position dyslexia, attentional dyslexia, and neglect dyslexia showing very clear dissociations between errors in reading words and errors in reading numbers. And not only in general, a problem in reading words, but not a problem in reading numbers, exactly in the same processes. So we look for letter position versus digit position. We look at migrations of letters between words and of digits between numbers. And we look at omissions of digits on the left versus omissions of letters on the left. And we see very, very sharp dissociations between word reading and number reading. So in general, what we did was showing good number reading and impaired word reading, but we also point with our fingers and say impaired letter position, impaired attentional dyslexia, neglect dyslexia without any problem in reading numbers. Okay, so this was this part. Dyslexia without dysnumeria. Now I'm going to talk a little bit about the other direction of the dissociation, creating a double dissociation. So now I'm going to talk about individuals who have a problem in reading numbers without a problem in reading words. So when we look at this, this is in general the situation that we're going to talk about, impaired reading numbers without problems in word reading. But again, I'm going to approach it in the exact same approach. So I'm looking very carefully what exactly is impaired in this person's problem in reading, in this person's reading of numbers. And I'm going to start with Nomi. Nomi is a signer, another signer of Israeli Sign Language. She's a signer from birth who came to us because she said, something is wrong with my number reading. I don't know what the problem is, but forever, when I was in school, I was always very poor with numbers. I don't know why. And when we tested her, indeed, she had a lot of errors in number reading, and the errors were very specific. She had what we call decimal errors. So instead of, if you look at the first example on top, instead of saying 985,000, she said 98,000. So it seems like she took a six-digit number and she put it on a hierarchy, on a template of 5 digits, for example. So there is something wrong about her creating a structure that will be appropriate for 5 and 6-digit numbers. It also affected her response times. So when we look at her reading of 5-digit numbers and 6-digit numbers, she was really, really slow. So in general, both when she had to read and sign written multi-digit numbers, when she had to have when we tested her number comprehension, she showed exactly the same pattern of errors. And also when she had to in the Israeli Sign Language, as I think in other sign languages, there is a parallel system where you don't have to use the morphological, so you don't have to say, 2,222, right? You can say 2,222, similar to how you would say your ID number, okay, or your telephone number. Usually when you say your ID number, you don't say it as a multi-digit number, you just state it number by number. So when she was only required to state or to fingerspell numbers number by number, digit by digit, without a structure, she had no problem. So there is something about her. So she perceives the number correctly, but then when she has to put it on the template, I'll show you when she had to create some kind of abstract decimal frame, this is where she fails, okay? I promise I will not take you through all the tests that made us conclude that this is where her problem is, but it's important to know that she has a very specific point of deficit in the number reading system that causes this deficit. And now we can ask whether she has the same kind of structural problem also in word reading. And she doesn't. Her word reading is completely normal. She doesn't have letter position errors. So if her deficit is somewhere in the beginning of the process, we would expect to see some kind of letter identity errors or letter position errors, nothing. She's completely within the control range for word reading. And when we only take the long words, again, no problem. Even in 11-letter words, we could find a few of them in Hebrew, no problem. So we have a double dissociation within sign language between word reading and number reading. We have Alon and Yona who had problems in word reading but not in number reading, and we have Nomi who has problem in number reading but not in word reading. So we see that there is, I think we can conclude that reading words and reading numbers use completely separate mechanisms. I'll mention maybe quickly that there are other cases that we found and many other cases that were found in the previous literature of dissociations between individuals who have dysnumeria, specific, sometimes very specific. So these are two sisters that we tested who have problems in the numerical visual analyzer, in the structural analysis of the numbers, without any problems in the analysis of letters in words. So this is a bit small, but they almost have no errors in reading words. They have a lot of errors in reading numbers. Okay? So again, a dissociation, problems in reading numbers without problems in reading words. And you can see that in a very long list of other selective impairments in dysnumeria. This is something that Dror Dotan and I summarized in a paper in 2019. But you can see very specific when you look at, this is the citation. If you look one process after the other within the process of reading numbers, you can see a deficit in reading numbers without a deficit in reading words, a deficit in reading numbers without a deficit in reading words. So what we have now is the opposite direction. We have good word reading with impaired number reading. And together we have a double dissociation between number reading and word reading, suggesting that there are two separate processes, one dealing with orthographic material, the other dealing with numbers. Okay. And now we get to the last part of today's talk. So we had dyslexia without dysnumeria. We had dysnumeria without dyslexia. And now we get to the very last part of the talk, where I'm going to show you individuals who have problems in both numbers and words, but they show different properties. Okay? And I'm going to talk about it, people who have problems in phonological output and people who have problems in phonological input. So this is a simple model that shows how important the phonological output buffer is. So what is the phonological output buffer? The phonological output buffer is a relatively late component that is in charge of preparing the words to phonological production. And what it does, it holds the phonemes and it assembles the phonemes. And it is crucial in all kinds of speech or sign production processes. So it is crucial in reading. So you get from a written word to the phonological output buffer to read the word aloud. It is crucial for lexical retrieval. When we see a glass and we want to say glass, we start with the conceptual system, but we get to the phonological output buffer in order to say the word. And it's also important for simple repetition of non-words. If we want to repeat the non-word punave, we have to hold this in the phonological input buffer and then repeat it in the phonological output buffer. So it's crucial for repetition, for lexical retrieval, for spontaneous speech, and also for reading. And as I said, it's a short-term memory component. It holds phonemes, and it assembles phonemes and also other kinds of units. And the question is, what kinds of units does it handle? So this is work that I did especially with Dror Dotan. This is the celebration of his submission of his master's thesis, I think. And I'm going to show you one patient who has a phonological output buffer deficit following brain damage. And he was very kind because I wanted to show these errors I wanted people to hear the errors also in English, because I know that Hebrew is sometimes dispreferred. So I asked him to name pictures in English, which is not his first language. Okay, and you will see the pictures that he had to name, and you will hear him naming them.
Umbrella?
It's not the original speed.
זה דרסל.
He's a very nice guy. And what you can see here is that it seems like he knows what the phonemes of the target word are, but he fails to assemble them and to organize them in the correct way. So you see that he has a lot of the phonemes of the target word, but they are not organized correctly. So this is very clearly phonological deficit, right? We see phonological errors when he tries to produce words. What happens? Yes?
In writing, you would have a problem?
He didn't have much of a problem in writing. specific, so it doesn't have to come with a writing deficit. Some do, but some don't. Okay, so what about now? So at the same day, we gave him lists of numbers and we asked him to read the numbers. And this is what he did.
3,390, 408, 100, 209, 750, 4,316.
Okay, so you can see that he makes errors, but the errors look completely different, right? We don't see phonological errors all of a sudden. He doesn't say instead of 6, seal or zix. He does something else. Instead of saying 6, he says 3. So what is going on here? It's the same person, on the same day, with the same deficit. In words, he makes phonological errors. In numbers, he substitutes one number word with another number word. So it means that these kinds of units are stored and handled differently. Okay. And so in general, we and not only us, a lot of groups before us were working with individuals with phonological output buffer impairment, and we see very consistently that there are phonological errors in words and whole unit substitutions in numbers or omissions. And when we look here, these are 5 in conduction of phasics, so individuals with a deficit in the phonological output buffer, and the light gray are whole unit substitution, so 4 to 6, and the black is phonological errors, so 4 to zor. And what you see is that in numbers they make whole unit substitution, substituting one number word with another number words, and in words they make almost only phonological errors. What we suggest is that it means that the phonological output buffer holds units of different sizes, of different kinds. So the phonological output buffer holds phonemes, but it also holds number words that are pre-assembled. So for the word for, it doesn't hold f, o, and r. It holds the whole number word for, and for the word 20, it holds the whole pre-assembled word 20. And then if we have substitution within this mini store, we might substitute r for t or f for l. But if we substitute a unit in the number word mini store, we will substitute 4 for 3 or for 6 or for 7. Okay? So this is the idea, that the representation of words and numbers in the phonological output buffer is different. We have units of different sizes. And this work continued, and in general what we found is that we have phonemes, we have number words, but we also have morphological affixes that are pre-assembled, and we have function words that are pre-assembled. And so we have 4 different mini stores. Each of them can have whole unit errors within this mini store, and this goes back to work by Laurent Cohen and Stanislas Dehaene on building blocks. So the idea is that morphemes and function words, morphemes are building blocks of words, function words are building blocks of sentences, numbers, digits, number words are building blocks of multi-digit numbers, and phonemes are building blocks of morphologically simple words. So this is what we find in aphasia after brain damage, but we find exactly the same and very commonly in developmental disorders. And this is the PhD of Revital Guggenheim. This is from her master's celebration, but soon we'll also have a celebration of her PhD. And she tested quite a lot of participants who have very, very poor phonological working memory, so very limited spans, very severe difficulties in repeating non-words and repeating words, in reading non-words, and manipulating phonemes. I'll skip the examples. And what we see is that when they have to produce words, and this is repetition, when they repeat words, what we see is almost only phonological errors. Okay? Almost no semantic errors. So they would not substitute a table for a chair. They will substitute table for cable or fable or navel. But when we present numbers, they make whole unit substitutions and no phonological errors. So exactly the same pattern that we've seen for the adults with the acquired impairment, we see also for developmental cases of phonological output buffer impairment. And the same for reading, phonological errors in words, semantic or whole unit errors in numbers. So we see exactly the same pattern also in developmental phonological output buffer impairment. And if we go to sign language, we see exactly the same pattern also in sign language. So we were working with individuals. This is another individual, not the one that I reported in a previous talk. A person who has a developmental deficit in phonological output buffer, who is a native signer of Israeli Sign Language. And we looked at her phonological errors, and we looked whether she makes phonological errors in words and whole unit errors in numbers. What are phonological errors in sign language? We talk about 3 parameters. The parameter of hand shape, so signs differ with respect to the type of hand shape. There is another parameter, place of articulation. Signs differ with respect to place of articulation. So this is a cow and this is yell. Okay? So they have the same movement and the same hand shape, but different place of articulation. And we have different movements. So this will be one movement, this will be one movement. So there are different kinds of movement. And this might be phonological. If someone substitutes a hand shape or a place of articulation or the movement, then it's a phonological error. Okay, so we talk about Zoe. Zoe is a signer, a native signer. And when we tested her spans, so her phonological working memory, we see that her spans are very, very limited. She can't repeat more than 3 lexical signs, not more than 1 non-sign, not more than 2 compound signs, and not more than 2 also in input signs. So she has a deficit in the phonological output buffer and a deficit in the phonological input buffer. How does it affect her production? Well, when she produces signs, she makes phonological substitutions. So instead of saying fly, she says fly. Okay? Instead of saying banana, she says banana. So she changes hand shape. Instead of saying a contraction, she says contraction. So not in the right place. And instead of saying white, she says white. You see the different movement? White and white. So we see phonological errors in signs. What happens when she has to sign numbers? This is what happens. Again, we see that she substitutes one number sign with another number sign. She doesn't make phonological errors. She makes number sign substitutions. Exactly as we saw in the cases of acquired phonological output buffer in spoken languages and developmental phonological output buffer impairments in spoken languages. So for phonological output buffer, what we see is, yes, both words and numbers are impaired, but they show different patterns of impairment. They are stored separately and differently. So I'm summarizing. We see, first of all, we saw dissociations. So we saw individuals with letter position dyslexia, attentional dyslexia, neglect dyslexia, without digit position migration between numbers or neglect of the left side of numbers. We saw the opposite pattern of dissociations. We saw individuals with specific dysnumerias in the structural processes, in the decimal template building, and in the other components that had no problem in reading words. And we saw that even when both are impaired in the case of phonological output buffer, there are different patterns of errors. And I think we can conclude that there are different processes that handle words and numbers. Thank you.